Bismillahirrahmanirrahim. Today our lecture is about analysis of statically determinate rigid jointed frames. uh, as you know that the two dominant planar structural systems are plane trusses and plane frames. Plane trusses were discussed in detail previously, and we went through its analysis using joint method and section method, and we solved two different examples. Also, you took some assignments, and I hope that you people will be able to analyze the trusses very well. Both structural systems are formed by connecting structural members at their ends such that they are in a single plane, right? Now, the systems differ in the way the individual members are connected and loaded, right? Loads are applied at joints for truss structures. As you remember, the assumptions we had made during the analysis of trusses that the members are connected together with a uh, pin jointed. The end conditions are pin joint, okay, and they cannot resist or restrain the bending moment. However, in the frames, the members are connected with a rigid joint, okay, and the bending moment is there. So consequently, in the truss members, the member forces were purely axial, if you remember. Either it was tension or compression. The frame structures behave in a completely different way, right? What is that way? The loading is applied directly to the members. If you remember, in the truss structures, the loading was applied only at the joints. However, in the frames, the loading is directly applied to the beam or column, resulting in internal shear and moment as well as axial forces in the members. So, in the frame elements or in the frame members, there is a axial force, there is a shear force, and there is a bending moment. Depending on the geometric configuration, a set of members may experience predominantly bending action. Okay, so those set of members that experience bending action predominantly, they are called as beams. However, the other set may experience predominantly axial action, and that set of members is called columns. So in frame, you have basically two different types of members. One is called beam, where predominant bending action prevails, and the other is a column where there are axial forces that prevails. The typical building frame is composed of a combination of beams and columns. Okay. Now frames are categorized partly by their geometry and partly by the nature of the member to member connection. For example, pinned versus rigid connection, right? Figure 1, which is here, illustrates some typical rigid frame planes using mainly for light manufacturing factories, warehouses, and office buildings. We generate three-dimensional frames by suitably combining these plane frames. Okay, so right now we are talking about 2D frames. If we remember this, we are talking about plane frame. Okay, so this these plane frames can be combined together to form 3D frames. Now look at figure A, a single bay frame and a single story. By meaning of single bay, I mean that there is only one bay. This is called the bay, the distance between or the area between the two columns. Okay, so this is one bay, and this is one story column. See, there is only from ground to this beam, there is only one story. So this is one bay, one story frame. Now this is three bays, one, two, and three. This is a three bay and single story column frame. Okay, now coming to here, this is three bays, one bay, two bay, three bays, and three stories, one story, two story, three story. So this is three bays, three story column, frame, I'm sorry, not column. This is the same frames just like C, but here we are putting braces, lateral braces, to make the frame more rigid. Okay, so if you apply a lateral force at a top floor of C and D, the deformation or the deflection in the C will be more than the D, because we are applying braces and putting constraints in frame D. Okay. Now, what is statical determinacy in planar frames? All the plane frames that we have discussed so far can be regarded as rigid bodies in the sense that if they are adequately supported, okay, right? And the only motion they will experience when a planar load is applied will be due to deformation of the members. So all these frames are planar frames, and these are regarded as rigid bodies if they are adequately supported. Okay, if they are not adequately supported, for example, if you remove this support, then this frame will be unstable. So one, if they are adequately supported, and the other thing is that if you applied a load on this frame and it experienced some deformation either in the lateral direction or in the vertical direction, right? Only after it experiences some deformation, then there will be a reaction in it. Okay, the only motion they will experience when a planar load is applied will be due to deformation of the members. Okay, so if the uh, uh, force is applied on a frame, then the deformation caused by that load will be the only motion that these frames will experience. Therefore, we need to support them with only three non-concurrent displacement restraints. Okay, if you remember the stability of trusses lecture, I explained over there that all the reactions should not be concurrent, otherwise the structure will not be stable. So it says that we need only three non-concurrent displacement restraints. We can use a single fully fixed support scheme or a combination of hinge and roller supports. So it is basically similar to that of beam supports. If you remember the supports of beam, it is more or less similar to that. Examples of adequate support schemes are presented in figure 2. All these schemes are statically determinate. In this case, one first determines the reactions and then analyzes the individual members. So this is figure 2. As you can see that this is a hinge support and this is a roller support. So a combination of hinge support and roller support gives you a complete set of reactions that are non-concurrent and that are sufficient to resist the displacements and the motion caused by the external loads. This is a frame and only one fixed support is here. There are three reactions: the vertical reaction, the horizontal reaction, and the bending moment. So as it says in the previous slide that we can use a single fully fixed support scheme. Okay, so this is fully fixed support scheme and these are the combination of roller and hinge in A and C both. So statical determinacy is evaluated by comparing the number of unknown forces with the number of equilibrium equations available. So the static indeterminacy of columns is almost similar to that of the beams. For a planar member subjected to planar loading, there are three internal forces, that is axial force, shear force, and bending moment. And we have three equilibrium equations: summation of f of x, summation of f of y, and summation of moments, right? Once these force quantities are known at a point, the force quantities at other point in the member can be determined using the equilibrium equations. So first we will find the reactions, and after that we will move forward to analyze the individual members. Figure 3 illustrates the use of equilibrium equations for the member segment AB. So just look at this member AB, right? Now if you can find the all the three reactions, for example the shear at B, the axial force at B, and the bending moment at B, then by equilibrium you can find it at point A as well. Okay, therefore it follows that there are only three force unknowns for each member of a rigid planar frame subjected to a planar loading. So for each member, for example member AB, member BC, or for example AD or DE, whatever you give them names. So if you find the three unknown forces for each member, then you can determine the whole you can analyze the whole frame. What are the analysis steps of statically determinate frames? The analysis strategy for these structures is as follows. We first find the reactions by enforcing the global equilibrium equations. Okay, first you have to find the support reactions. This is your first step. Once the reactions are known, we draw free body diagrams for the members and determine the force distributions in the members. Okay, so after reactions, you draw the free body diagram for each member and then determine the forces in the members. We define the positive sense of bending moment according to whether it produces compression on the exterior face. Okay, I will show you on the next slide the positive sense. The sign conventions for bending moment, transverse shears, and axial force are defined in figure on next slide. Okay, and after that we will solve some examples so that you have got a clear idea of solving the plane frames. Now consider this frame A, B, C, D. The member CD is inclined, AB is vertical, and BC is horizontal. A load, a lateral load, a point load of A is applied at joint B, and uh, a distributed load, whether uniformly distributed or uniformly varying load, is applied on a member BC, which is beam. Okay, now as you know that the roller support D is a roller support and it gives only one reaction in the vertical direction, and A is a hinge or pin support and it gives two reactions, one in vertical direction, other is horizontal direction. Okay, so RA in X direction and RA in Y direction are two reactions, and RD in Y direction. So one, two, three. You have three unknown reactions and you have three available equilibrium equations. So by using summation of moment at A is equal to 0. So you are making it 0, making it 0. So you will get reaction at D. Once you get reaction at D, you can use summation of f of x. So there is only one this unknown and one this applied force. So you can find Rax. And using summation of f of y, you already know Rd. You already know the applied load. So you can find Ray. Okay, so it is very simple, just like the beams, but you have to be more careful as the bending moments and the directions will be different. Now look carefully over here in this part. You will be knowing the sign convention for axial force, bending moment, and shear force. Okay, so look at that in member AB. The so this sign convention will be positive. For example, the joints are in compression. See, these forces are making joint A and B in compression. So we are taking it as a positive. If it was opposite and it was upward over here and downward over here, so it would be negative. Similarly, these forces are making joint B and C in compression. And similarly, these forces are making C and D in compression. So for axial forces, if the forces are making the joints to be in compression, then you have to take it as a positive. Okay, now coming to the bending moment. So if it is outward, see, if the bending moment is causing outer side, this is the inner side of the column and this is outer side, so it will buckle like this, right? And it causes compression in outer phase. So as it says here that positive sense of bending moment according to whether it produces compression on the exterior face. So this sign convention is producing exterior compression on exterior face, this produces compression on exterior face, and this produces compression on exterior face. Okay, so these are taken as positive. Similarly, shear force, so these directions will be taken as positive. Now the example number one, unsymmetrical cantilever frame. This is a cantilever frame. You can see that there is only one fixed support. What you have to determine is the reactions and draw the shear force and bending moment diagrams. So what is solution? We first determine the reactions at A. Okay, this is A. We have three unknowns: vertical force, horizontal force, and bending moment. And for simplicity, let me see if I can use something. Okay, I have to go to the slideshow for that. uh, So once you determine the reactions at A, then the shear and moment at B can be figured out. Okay, these results are listed in figures on next slide. Once these values are known, the shear and moment diagrams for members CB and BA can be constructed and the final results are plotted then. So coming to the solution, using the equilibrium equations, summation of f of x is equal to 0. So if you check the frame, original frame, there is no force in x direction, right? No applied force. So this reaction in the x direction will be 0. Okay, see Rax is equal to 0. You have no reaction. Now, using the other equation, summation of f of y. So this is your load in y direction, 15 kilonewton. And how much is the distance? 2 meters. So 15 into 2, 30, right? So Ra is in upward direction and 15 is in downward direction. So Ray minus 15 into 2 is equal to 0. There is no other vertical force. So Ra is equal to 30 kilonewton. Similarly, summation of bending moment at 0. So Ma, which is the resistive moment at A, minus this 15 into 2 is the force, and what is the perpendicular distance? 1. So the bending moment will be 30 kilonewton, and it will be in counterclockwise since the applied moment will be in clockwise. Sorry, the applied moment will be in clockwise, so the resistive moment should be in the counterclockwise. Okay, uh, I will stop this video at the end of this example, and from the next example I will switch to the full screen mode so that I can draw on screen for your convenience. Okay, so don't worry, from the next example you will get some more clear picture. Now once you determine the reactions, you know that there is no horizontal forces, no horizontal reaction. The vertical forces, the vertical reaction is 30, the bending moment is 30. So now you have to analyze this column and this beam. Now what will be the strategy, from where you should start? This is the most important question. Okay, so keep in your very mind that you have to start from the weaker member and move to the stronger member. So first you take the weaker member and analyze that member, and then shift its forces and moments to the stronger member. So which one is weaker and which one is stronger? Let me show you. This is your frame, and this is the beam, and this is column. Now look carefully. Is there any support under your beam? No. The end C of your beam is hanging in the air, right? It is hanging right over there. However, look at the column AB. The and A of the column is fixed. The fixed support is the strongest support. Okay, so your column is the strongest member and your beam is the weakest member in this frame, since we have only two members. So you have to start from member BC. Okay, bring everything to point B of this beam, and then go to the column and transfer everything from B to A. Okay, so this is your member BC. Since this you cannot resist anything over here, right? C is freely hanging in air, so you have to resist all the forces and movements at point B. So what is take this as okay, let me show you. This is your analysis of beam. Let me make it more visible for you, right? And hmm. So this is your analysis of beam. You are resisting all the vertical load at point B. So what is your total vertical load? 15 into 2 meters. So 15 into 2, 30. So 30 kilonewton is acting downward, right? So you have to resist it. Summation of f of y. So summation of f of y means 30 kilonewton in upward. So you have to apply it at point B, right? Now you are done with the f of y. There is no f of x. The third one equation is summation of moment at point B should be 0. So the moment acting to this side is 15 into 230 into 1. So 30 kilonewton meter moment is applying in the clockwise direction. So at joint B, it should be in the counterclockwise direction. Now please keep in mind that this rigid jointed frame is not like trusses. In the trusses, there was no bending moment at points where the two members were meeting. Okay, but this is a rigid jointed frame, and what does rigid jointed frame means that your joints are resisting the bending moment. Since we are calling them as rigid joints, so we consider it as a fixed support. Okay, as a fixed joint. So that's why your joint is resisting the vertical load as well as bending moment. Now, once you have analyzed it, see all your equilibrium equations are satisfying this portion. Then you have to move to your column and take it to your column. At joint B, now you have to first analyze. First, you have to make your joint B in equilibrium. First, you have made your beam BC in equilibrium, right? And this was the result. Now you have to make your joint B in equilibrium. So at joint B, 30 kilonewton was acting upward, so you applied 30 kilonewton downward. So this downward and this upward, it cancels each other, and the joint B is in equilibrium. Similarly, here 30 kilonewton meter bending moment was applied in the counterclockwise direction. So you apply here as a clockwise direction, right? So first you made your joint in equilibrium. If it is in equilibrium, just compare the joint B in the beam and in the column. Okay, then move to the analyzing your member AB. Now, in member AB, 30 kilonewton is acting downward, so you have to apply 30 kilonewton upward, summation of F of y. And summation of moments, 30 kilonewton is applied in the clockwise direction, so you have to apply 30 kilonewton in the counterclockwise direction. Since this is fixed support, it gives you reactions in all the directions. Now compare the reactions with the original one, which you have got it with the global equilibrium equations. So 30 kilonewton upward, 30 kilonewton upward, 30 kilonewton meter counterclockwise, 30 kilonewton meter counterclockwise. No RA in X direction, no in X direction. Okay, once you get these results and it matches the original results, it means that your process was okay, and you are good to go. So then coming to the shear force and bending moment diagrams, since in column there was no shear force, see, there is only axial force and bending moment. But in beam there is shear force and there is bending moment. So in beam you have to draw the shear force diagram. This is your shear force diagram. You are starting from this point, the weakest point, coming to the strongest point, and here the reaction is making it 0, right? So from 0 you are coming down to 30, and the 30 force at here making it 0 again. So this is your shear force diagram for the beam, and there is no shear force in the column. And similarly in the bending moment diagram in beam, so from shear force diagram, if the shear diagram is 1 degree, then the moment diagram will be 2 degree, and you know the magnitude, 30 kilonewton magnitude, so it is like this. And similarly sorry, there is a 30 kilonewton constant bending moment in the column. See, you have 30 kilonewton here and it is supported over here, so in the entire column there will be a 30 kilonewton uh, meter bending moment. So this will be a 0 degree bending moment diagram, right? So this is how you get a 0 degree bending moment diagram when you have bending moment at one end and it is resisted by bending moment at other end. Okay, so if you get something like that in the paper or in the assignment, don't get confused. Okay, so we are done with the example number one, and I'm stopping this video just because that in full screen mode I can draw on the screen for your better understanding. Okay, so stay tuned for the second video. Thank you.